Welcome back. We now look at the variance of the sampling distribution of the sample mean. So if we have a random sample which is done with replacement from a finite population, or if we pick a random sample from an infinite population, then the variance of x bar would be sigma squared divided by n. And so the standard deviation of x bar would be sigma over root of n, which is the square root of the variance. So where n is the sample size. So x bar is the sample mean. So let's prove this. So the variance of x bar is the same as the variance of, so what is x bar? X bar is the sample mean, which means it's the following: x1 plus x2 plus dot 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 plus xn divided by n. Now, so the variance, according to a formula that we have done before, this variance can be expressed as the variance of x1 plus the variance of x2 plus dot 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 plus the variance of xn divided by n squared. And this step can only be done if these variables x1 up to xn, they are independent. And they will be independent if we are picking a random sample with replacement. That is, imagine that you randomly pick an object. Well, let's go back to the example of height. So if you pick a male randomly to observe his height, and then in the second observation, the person that you picked in the first observation may also be picked in the second observation, and so on. So that's with replacement. Without replacement means that once you pick a person and observed his height, he's not going to be picked in the remaining observations. And then if you have a random sampling from an infinite population, that doesn't really make sense. That's not an important issue, because the likeliness that the same person will be picked again for another observation is very slim. So in both of these cases, with sampling with replacement or sampling from an infinite population, this observations x1 up to xn, they will be independent. So then we can express the variance of the ratio x1 plus x2 plus dot 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 plus xn over n as the ratio where we are summing the variances of the individual observations divided by n squared. So now the variance of x1 is sigma squared, which is the population variance, and variance of x2 up to variance of xn, they are also all sigma squared. So again, that's because if you are thinking, again, let me explain this by using the example of height. If we, x1 is the first observation, that is, you're picking a male randomly and observing his height. So the distribution of x1 should be the same as the distribution of the population. And so the variance of x1 should be the same as the population variance. And so what we get here is that n sigma squared divided by n squared, and that's equal to sigma squared divided by n. So we obtained the result that the variance of x bar is sigma squared over n, and of course the standard deviation is just the square root of that. Okay, so we now know the variance of the sample mean to be sigma squared over n, where sigma squared represents the population variance. Now, if the random sample is done without replacement from a finite population of size capital N, then the variance of x bar turns out to be sigma squared divided by n times capital N minus n over capital N minus 1. Small n is the sample size, capital N is the population size. Now this term in parentheses is called the finite population correction factor, or in short we say FPC. So let's say a few words about FPC. When n is 1, the FPC is 1. So in this case, the distinction between with and without replacement is not important. And if n is greater than 1, then the FPC would be less than 1, in which case precision is greater for the case of without replacement sampling. And then as n gets closer and closer to capital N, the FPC goes to 0. In other words, the standard deviation of x bar goes to 0. And when n is much less than n, capital N, then FPC would be about 1. And the distinction again between sampling with and without replacement is not going to be important. So when n is much smaller than capital N, we can assume that the variance of x bar is sigma squared over n again. So from now on, we're going to assume that either our population is infinite or our sample size is much smaller than the population size capital N, in which case we can assume that the observations are independent and that the variance of x bar would be sigma squared over n. So from now on, this is the variance that we assume. So recall that the variance is a measure of variability. So variance is a measure of how spread the values of x bar tend to be around their mean, around the population, around their mean mu, which is the population mean. So we may think of variance of x bar as measuring the precision of x bar as an estimator of the mean mu. So in that sense, we use the notation SC of x bar, or called a standard error of the mean. That's pretty much the standard deviation of x bar, which is the root of variance of x bar. So since the standard deviation of x bar is sigma over root n, we see that the precision of x bar as an estimator of mu improves with increasing sample size n. However, the larger the population standard deviation sigma is, the less precise x bar is as an estimator of mu. So to get a good approximation, if the population standard deviation sigma is small, then you don't need a big sample size. But if the population standard deviation is big, then you need a bigger sample size to have a good approximation of the population mean from the sample mean. Okay, so I'm going to end this video here, and this is all I have to say about the sampling distribution.